So, today I will demonstrate the resistivity measurement of metal and semiconductor as a function of temperature. So, how resistance of a metal and semiconductor changes with temperature. So, this is one fundamental experiment in the sense that how to distinguish a metal from a semiconductor. So, from this experiment we can distinguish between the metal and semiconductor. So, in that sense this experiment is very important. So, resistivity is known as specific electrical resistance or volume resistivity. So, resistivity rho is equal to R A by L ohm meter. So, R is resistance of the sample, A is the area of the sample and L is the length of the sample, then rho is the resistivity. So, resistance and resistivity, the difference is that resistance depends on the dimension of the sample, but resistivity is independent of the dimension of the sample. So, resistivity is basically resistance of a sample of a cube having unit length, unit breadth and unit thickness. Okay. So, that is why it is here R is resistance ohm, R is resistance in ohm, and if A area is 1 and length is 1, so this say meter square and this is the meter, so it will be meter. Okay. So, for unit, that is why it is called volume resistivity. It is basically for unit volume of a material, what is the resistance. So, that is called the resistivity. So, now resistivity depends on temperature. Generally we write the expression of resistivity as a function of temperature. Rho T is equal to rho 0 1 plus alpha T minus T 0 plus beta T minus T 0 square plus, so higher terms will be there. It is a polynomial. Okay. So, for different range of temperature, so one will take up to first order or second order or third order terms. So, that one has to decide. So, that is why it is not just straightforward linear function. So, it depends on higher terms also. So, but in general one can write this polynomial. So, here you see, if we take just only this first order term 1 plus alpha T minus T 0, then T is the temperature, present temperature, and T 0 is the initial temperature. So, it can be room temperature or it can be some other temperature. So, at initial temperature what is the resistivity? So, that is the rho 0 and that temperature is T 0, and now I am changing the temperature from T 0. So, it is T, it is it can be higher temperature or lower temperature. So, generally T, if you increase the temperature, so T minus T 0, this term will give the change of temperature delta T. So, for this change of temperature, okay, what will be the resistivity? So, rho 0, that is the initial resistivity plus alpha, rho 0 and this delta T. So, that part is basically is the change of resistivity due to the change of temperature delta T. Okay. So, now here alpha is the temperature coefficient of resistivity. So, temperature coefficient of resistivity, if it is positive, then you can see this. So, this term will be added with this rho 0 term. So, that means this term will be positive, and resistivity will increase with temperature. Okay. If this alpha, it may happen that alpha is negative, okay, temperature coefficient is negative, then this term will be for increasing temperature by delta T, this term will be negative. So, resistance will decrease. So, with increasing of temperature, resistance will decrease. With temperature, resistance is decreasing, or with temperature, resistance is increasing. So, that will depend on the alpha, the temperature coefficient of the resistivity. So, in case of metal, this alpha is positive, and in case of semiconductor, this alpha is negative. Okay. So, but this is a polynomial, you know, it is not just, it does not depend only this up to first order. So, there is the effect of other terms also, it is a polynomial. So, it comes in various form. In some cases a logarithmic form, it can be exponential form. Okay. So, here just this expression I am using just to tell you that from this expression in some extent, okay. So, considering the main terms, one can decide whether temperature will increase or temperature will decrease. That will depend on the material, that will depend on the temperature coefficient of the resistivity of that material. And if it is positive, generally in case of metal it is positive, so it will temperature with increasing temperature the resistivity will increase. In case of semiconductor, this alpha term is negative, temperature coefficient is negative. So, the resistivity will decrease with increasing temperature. Okay. So, that's what we can conclude, but exact form when you will do experiment, it will decrease and other one will increase, but in which form it will increase or in which form it will decrease. So, that we cannot get from here as long as. So, basically we can feed this experimental data and find out the fitting parameters. So, how it depends on temperature. So, it will depend on the other higher terms also, okay, depending on the range of the temperature. So, this form will be different. So, temperature dependence will be in different form. Okay. So, that we can find out from the fitting the experimental data of resistivity versus the temperature curve. Okay. So, why we are doing showing the experiment using the metal as well as the semiconductor, because from this experiment one can easily distinguish metal and semiconductor. In case of metal, as I told this, it will increase, resistivity will increase with temperature. In case of semiconductor, resistivity will decrease with temperature. So, this is the fundamental inherent phenomena of the resistivity of metal and semiconductor, and one can distinguish them seeing the response to the temperature. Okay. So, now question is that in case of metal, resistivity or resistance of the sample increases with temperature, and for semiconductor it decreases with the temperature. Okay. So, why this opposite phenomena we see? So, reason is that the metal have the free electrons. Okay. So, carrier are available in the metal. Now, this carrier, when we apply voltage, so carrier will move. Now, when it is moving, carrier will move in a particular direction. Okay. In which direction? The direction of the electric field, direction of the applied voltage. Now, when the electrons are moving towards the following the electric field, then it will collide with other electrons, it will collide with the impurities, if any impurities in the metal, it will collide with the ions. So, generally we do not tell ions, so we basically here major contribution comes from the scattering, this electron phonon scattering, from electron phonon scattering, this resistivity arises in case of metal. So, what is phonon? Actually, when you increase the temperature, change the temperature, the lattice it vibrates. Okay. So, there will be lattice vibration, So, this quantized form of the lattice vibration is basically phonon, So, as if this in metal there will be phonons, which is the equivalent which generates from the lattice vibration. Now, electron, so electron will be scattered from the phonons. So, instead of instead of telling that this electron will scatter from the ions, instead of that, so we tell that electron will scatter from the phonon. So, phonon is nothing but the quantization of the lattice vibration. Okay. And this lattice vibration is basically become prominent, or it changes with the temperature. So, scattering will be higher and higher when temperature will be higher and higher, because you will get the phonons, higher number of phonons from the lattice vibration, and there will be more scattering and there will be more resistance. So, that is the reason for the resistivity or change of resistivity or resistance of a metal with temperature. So, in case of metal, why these free electrons are available? Why we tell these free carriers are available? Because if you consider the band structure of the material, so you have conduction band, then you have valence band, and these other bands are there, all other bands are filled up. Only this conduction band, in case of conduction bands are free, so valence bands also filled. Okay. Now, in case of metal, this conduction band and valence band, they overlap. Okay. So, carriers available in conduction band, electrons available in conduction bands, then we tell it is free. There is no bonding, it is free to move. Okay. So, in case of metal, the conduction band and valence band, they overlap. So, that is why this whatever the electrons are in the valence band, they are in the conduction band. So, they are free to move. So, that is why in case of metal we tell there is the free electrons are available. Okay. So, now in case of semiconductor, the conduction band is empty and valence band is filled. Okay. So, there is a gap between these two. So, there is no carrier available for the conduction. There are no carrier free to participate in conduction. Okay. So, now at lower temperature T0, okay, initial temperature, if it is small, if it is less than room temperature, or it is say, yeah, it is close to the zero temperature, 0 degree Kelvin. Okay. So, then it is just perfectly insulator. When you increase the temperature of the semiconductor, what happens? The carriers, the electrons from the valence band, so it will break the bonds, covalent bonds due to this thermal energy, and it will jump to the conduction band. So, now carrier is available in conduction band to participate in conduction. Okay. So, if you increase the temperature, the carrier density in the valence band and the conduction band. So, electron in conduction band and hole in valence band. So, two types of carrier will be generated and both carrier will participate in the conduction. Okay. So, with temperature we are increasing the density of carriers, free carriers. That is why, and that carrier, if you apply the voltage, so it will move. So, increasing the temperature, you are generating more number of carriers, so conduction will be higher and higher. So, resistivity or resistance will decrease. Okay. So, in case of semiconductor, so temperature is basically changing the electron and hole density, carrier density in the metal, it is increasing. So, that is the conductivity is increasing, resistivity decreasing, resistance decreasing. So, that is why in case of semiconductor we see that resistivity decreases with temperature. Okay. So, that is the change of resistance or change of resistivity of a metal and semiconductor as a function of temperature. So, this concept is simple, but this is the intrinsic property of the material, and experimentally we can easily verify. So, I will demonstrate this experiment in our lab. Thank you.